one of the biggest issues that's going to happen in Chapter 9. So Chapter 8, it's not as big of a deal because you're just looking at changing what you might specify as your traditional unit. Okay? You're looking at atoms, molecules, grams. As a unit goes, we've dealt with those kind of conversions before. It's not that big of a deal. Chapter 9 makes it a bigger issue, and instead of having just that first kind of measurement, if you will, unit, we have a substance unit that also tracks with it. You have to treat your unit now as not just that grams, but grams of something. Okay? Which means when you go through and do your units, you have to make sure that that translates across. So for instance, and you see the calculation shown up here, which I know is a little bit out of place. We've got a unit of moles, our measurement or our count, followed by the substance. When we go through to do our conversion, again, the unit of the amount followed by the substance. Why is it important to include the substance? Well, what happens if we don't include the substance? Okay. Take it even worse, don't include the substance. I need 0.5 moles. The unit I'm trying to get to is moles. What would the answer be? Sure, it looks like it's 0.5. Okay. You need the substance there to go through and do these conversions. That's what Chapter 9 is huge on, is specifying that substance and going through and doing those conversions. Okay. There's multiple different ways to organize how you decide to go through and do those conversion factors. One version is up here. This one, I would argue, isn't as useful because we're starting with atoms or molecules. And outside of Chapter 8, you really won't see that all that often because can we count atoms or molecules? No, we can't see them. So it doesn't really make sense to use that as a unit other than just conversions. Okay, so it's a bit silly in that respect, but that's what it's there for. Okay? After that, you can then convert your atoms or molecules into a mass unit. Okay, to get that conversion, so what we're looking at is that first arrow back and forth. We're relating a mass to a number, okay, or a count of things. Where can we find that information? Your periodic table gives you that information. So you'd have to make reference to the periodic table to go through and find that, okay, and be able to process it from there. That sets up your conversion factor. Okay? What we'd be looking at is a mass per, in this case, atoms. Okay? That allows me to now convert atoms over to mass. What if I wanted to know the number of atoms? Well, I can use effectively that same conversion factor, just flip it. Atoms over mass. Okay? You need to make sure that you track the number appropriately with it. When we look at the periodic table, let's say nickel, what's its atomic mass? For nickel, 58.69. So it gives us the number. What are the units associated with that number on the periodic table? AMUs, which is, again, kind of a crappy unit. Let's push that a little bit further. Careful, we aren't there quite yet. With AMUs, we can represent that as a mass unit per nickel atom. Okay? Again, it's an awful mass unit. Why? When you go in to use your instruments, your balances, do they measure in AMUs? No, they measure in grams. Okay? So this is where Avogadro's number came in handy, and that's ultimately what's happening in your AMU to gram conversion, though it's a little bit hidden. Okay? We can convert between those two different masses using the conversion factor 1 AMU equals that 1.66 times 10 to the negative 24th grams. Okay? Where is that conversion factor found? There's two big places that you could potentially find that conversion factor. On the exam given to you, or you had it memorized. It's in your brain. Where did you go? There you go. Okay? So you need to be aware of what's happening with that number. Okay? And where to find these conversion factors. we would now be at grams for our A. If we want to convert into moles of A, we're again relating a mass to a number. Okay? Now the mass that we're relating, the unit, is grams per mole. Turns out that this first place where we saw mass related to a number of something on the periodic table is also the same place that we can find the gram to mole relationship. Where is that? Where do we find it? Periodic table. So if we go to nickel now again, 58.69, we said the units on that could be AMUs. When we're using it as the AMU unit, we're trying to convert between that weird mass unit and a number of atoms. If we now want to relate to grams, what we can end up saying is that 58.69 is the number of grams in 1 mole. We now have the ability to convert between grams and moles. Okay? So when we write out the number off of our periodic table, so everybody at home can see this, 58, what did I say it was? 69. So if we've got nickel on our periodic table, there's our little symbol. That number means 58.69 grams in 1 mole. That is how you should be interpreting and writing that number. Okay, why? Because that sets up that unit conversion, gives you that unit factor that can allow you to solve problems in a dimensional analysis method. You will also see it written out as 58.69 grams/moles. Why is that written like that? What's the difference between them? They are exactly the same thing. There is no difference between them. So why would we write it grams/moles as opposed to grams over moles? Comes back to typewriters, ultimately. Which is easier to write in the typewriter? The grams/moles, because we can do that in a single line. We don't have to do a whole bunch of returns and shifts around. Okay? That is starting to change because technology is nice and we can actually format these things pretty quickly and efficiently without having to do that slash thing. So eventually that will disappear, hopefully, because it's an awful way to represent it. Okay? That allows us to convert to moles, in this case of A. We'll notice that the next conversion is to do what? Moles to moles. Oh, well, they're exactly the same number, but it's the moles of A to the moles of B. We've changed the substance. To be able to change the substance, we have to have a balanced equation, because the balanced equation is what's going to tell us the relationship between A, one substance, and B, our other substance. Okay? So when working with any of the questions that we're going to see in today's slides, we have to make sure that we have a balanced equation to be able to do that conversion. Without that balanced equation, we cannot convert into the other species. The only way we can convert to that other species is by looking at our moles, a count. Okay, we typically use moles, but we could also use molecules, atoms. Okay, why? A mole is just a very large number of atoms or molecules. Okay? So the plan is to ultimately start on one side and push it all the way to the other side. Okay? A complete switch in the units. Okay? Once we're now into moles of B, we can convert to the moles or grams of B, AMUs of B. We'd use the exact same idea of our conversion factors, except instead of them being conversion factors for A, which they were in the first part, we now have to use the conversion factors for B. Okay? Which means when we go to the periodic table, we don't look up the molecular weight of A, we look up the molecular weight of B. Okay? Kind of makes sense. I know that's very generic. There's not really any problems associated with that yet. Okay? Yeah?
With the
Avogadro's number?
The 6.2 times 10 to the 23rd is what? Is that the...
So Avogadro's number. So when you think about that, you should be thinking about it as a number. Avogadro's, whoops. Okay. What that's going to relate is the number of something to the number of something else. Okay. Avogadro's number, the big reason this is cool is because he went through and said the number of random items, which could be atoms, molecules, compounds, formula units, particles, okay, a count of something physical equals 1 mole. So the number we would put in front is our 6.022 times 10 to the 23rd. Okay. It's written as items because if I wrote atoms, now everybody tells me, well, I can't solve for molecules. Okay. Items can be molecules, atoms. It's any physical number of things, counting of things. Okay. It is not directly a measurement, and that's where it gets a little bit weird. Okay. Mass is a measurement. We go and put that on the balance. Okay. An instrument tells us that value. Okay. When we're looking at a number of items, we get to count it. So it's not really a measurement, sort of. Okay. Does that cover your question?
I just wanted to know if it was, the number was a mole and then it was 1 molecule.
It's always 1 mole. Yep. 1 mole and then some number of items. Okay? Other questions with that? Outside of Chapter 8, Avogadro's number becomes ultimately useless because now we actually start to deal with a scale that makes sense. We deal with grams and moles. To get into the gram and mole unit, we had to use Avogadro's number to get up to it. But once we know that our periodic table gives us grams and moles, we don't have to worry about Avogadro's number anymore. Okay? So treat it as a conversion factor like you would everything else. So our balanced equations. Okay? This is ultimately the big lesson within Chapter 9. The rest of it is applications of both Chapter 8 and 9. What we're looking at with a balanced equation is allowing us to convert between substances. We're starting with nitrogen and oxygen, and I can now convert that to nitrogen oxide or nitrogen monoxide. That's what that equation tells me. So if I start with 1 molecule of nitrogen and 1 molecule of oxygen, I can make 2 molecules of nitrogen monoxide. The numbers in front are where we're pulling that information from. Okay? If there's nothing written there, it's 1. So to be able to do everything within Chapter 9, you have to be able to do everything within Chapter 7, which could push all the way back to everything within Chapter 6. Okay? You have to be able to build on all of that information. It's not its own separate unit. Okay? When we look at all the possible conversion factors, since I happen to remember this one was a typo, our lower right-hand corner, there are 2 moles of nitrogen monoxide to 1 mole of oxygen. Notice with this single equation, we got 6 different conversion factors. So depending on what we were trying to do, we would use a different conversion factor. All of them are ultimately coming from the balanced equation. If I want to relate, say that first one, moles of N2 to moles of O2. Go to the balanced equation. What's the number that shows up in front of N2? 1. The number that shows up in front of O2? 1. The numbers that we need to write down in our conversion factor are 1 and 1. Okay? This conversion factor, does it really have anything to do with what you started with? No. Okay. Each of these conversion factors are something that are derived solely from the balanced equation. Which one we decide to use is going to be dependent on the rest of our other information. Okay. But that information can be derived using the unit formation that we've been talking about. Write down what you're trying to get to, write down where you start, and slowly start piecing it together to try and get there. Okay. So, should I give an equation on this? How many moles of oxygen react with 2.25 moles of nitrogen, given this equation? Okay. First thing that we should go through and do before we even start worrying about dimensional analysis, we need to make sure our equation is balanced. Okay. We might be able to zoom in and realize that we need to balance it because we're starting with moles of oxygen and ending with moles of nitrogen. To be able to convert substances, we must use the balanced equation. So it's not a bad place to start. We can check it, verify, is the equation balanced? Yes. So now we can start with our dimensional analysis. Where do we always start our dimensional analysis problems? Where we're trying to get equals. What are we trying to get? Good call. Moles of oxygen. Okay. In this case, it's not specifying oxygen atoms. We're asking for moles of oxygen. It's going to be implied. We're looking at that O2. What do we start with? Moles of N2. Okay. I won't put any numbers in this until I have some more information, or typically I won't put any numbers in until I'm satisfied with the units that I've got. Okay? Moles of N2, there's really nothing fancy with that, so I can go ahead and slide that number in. What number do I put in front of the moles of N2? Why do I put 2.25 and not 1? 2.25 is what we were given. Okay? We aren't looking at a conversion factor, that's what we're starting with. We can now move into our conversion factor. Okay, well, we're going to decide if we need a conversion factor. What were we given? Moles of N2, and what do we want? Moles of O2. Is the unit the same? No. So do we have the answer? No, we have to work for it. So start off with our conversion factor. Okay. As we've been discussing this, get rid of the unit that you don't want first. So the unit we don't want is moles of N2. How do we get rid of that? Put it on the bottom. Moles of N2. Okay. Okay. What unit do we want? Moles of O2. Okay. Do we have a way to relate the moles of O2 to the moles of N2? Yes. Where does that come from? The balanced equation, the coefficients from our balanced equation. What number shows up in front of our O2?
1.
What number should show up in front of our moles of O2?
1.
What number shows up in front of N2?
1.
What number should show up in front of the moles of N2? 1. Track your track your units. The moles of N2 cancel. We'd be left with moles of O2. Is that the answer we want? What does that mean? Punch it into the calculator, you've got your answer. In theory, this is one that you could do in your head, and our answer would be 2.25 moles of O2. Yes? Isn't it 2? Where do you see oxygen? Is that oxygen?
Oh.
So you got to be very, very careful with what you're referencing. That has oxygen in it, but that is not oxygen. What is that? That is nitrogen monoxide. Yeah. Okay. Should we make it a little more challenging? Before we make it really challenging, which is, I think, the next problem. I want moles of nitrogen monoxide. Okay, we're still starting with 2.25 moles of N2. Does that equal moles of nitrogen monoxide? No. So what do we have to do? We have to convert. What unit do we want on the bottom in our conversion factor? Moles of our N2. Why do we want N2? So it cancels the unit that we already have. What unit do we want on top? Moles of our nitrogen monoxide. Okay? Here's the next thing that I'm seeing a lot of people getting tripped up on. Does it matter that I start with 2.25 moles of N2? No. All I care about right now is that conversion factor. So if I had any easy way of covering up every other thing within this problem, I would. Okay, I don't, so we're just going to have to deal with it. Okay? The only thing we're concerned about is the relationship between those two. What is the relationship between those two? The number in front of nitrogen monoxide in our equation is
2.
What number shows up in front of the moles of nitrogen monoxide? 2. It's got to be 2 because that's the number that's directly from our coefficient. Okay. What number shows up in front of the moles of nitrogen in our equation? 1. So what needs to show up in front of the moles of nitrogen in our calculation? 1. Okay. It's directly coming from the balanced equation. There is no shuffling of numbers, anything like that. It's just the number in front equals the number in front, all the way through. Now when we go through and solve, what's our answer? 4.5 moles of nitrogen monoxide. Okay? There's no questions of do I need to multiply or divide unless there's a confusion with the dimensional analysis format. Okay? Is everybody comfortable with the dimensional analysis format as far as multiplication division goes? Okay. So let's make it a little bit more challenging.
I have a question about this.
Yes.
Does sig figs matter with this?
Yes. Yes, sig figs absolutely matter. Kind of, sort of, not really. It is something in every single calculation you should absolutely watch your significant digits. At this point, you won't have to worry about that unless you're directly being asked it. Okay. When you move into 151, I'm fairly confident that the only instructors, at least at this campus, the Pecos campus, are very strict with sig figs and will allegedly beat you to death with sig figs. Okay? So you'll need to watch out for that in the future. It won't be as big of an issue here. And even when they seem to care so much about it, I don't think they fully understand that they aren't really testing on sig figs in most of their problems. Okay? So if you see a sig fig statement, absolutely be aware that you need to watch out for it. Other than that, you're probably okay to just not worry about it. Okay. So before we can read this problem out first. What is the mass of mercury sulfide produced from the decomposition of 1.25 grams of mercury 2 thiocyanate? Yeah. So we've got the equation given to you balanced. You'll notice there's a little YouTube video here, which I should have set up already, but I didn't. Anybody know what's happening with this? These chemicals sound familiar? Of course, it's probably going to, oh no. Let's jump to, so that is mercury thiocyanate that they're laying out there. What we're looking at is a decomposition reaction. So to decompose it, what do we need to add? Heat. What ends up happening when we end up heating this? Gets all sorts of crazy weird and starts to do this odd growing thing. This was allegedly something that, and you might still be able to find it as Pharaoh's snake, I think is what it's referred to as a firework. So you can buy it and it does this little growing thing when you burn it. Any ideas why that's not something that we typically find anymore? Anybody know anything about mercury? Really, really toxic. Typically not a good idea to expose people to it. Okay. So while this thing does some cool stuff to actually watch, you're also releasing potentially mercury vapor into the air, and that's not a particularly good thing to be breathing. Okay, so it does some kind of fun stuff. Does this weird growing thing. Sometimes it looks cooler than others, but it's at least kind of neat. Right? Yeah? What's that?
Anybody else expect this kind of stuff in the lab?
Well, maybe we'll do it for 4th of July. If you're here for summer, maybe that's something that we'll do. I'll talk to the department, see what they can get running. So if we take a look at, Why is my screen not cut up? So if we take a look at that equation, remember the mercury is an issue. One of the big reasons that this thing actually grows and changes shape like that is that one of the products is a gas, and some of the other products are solids. So what ends up happening is the gas bubbles up inside it. When the solid is in its molten state, the solid really quickly cools, or the molten state cools and becomes a solid, and that gives you that kind of column shape because of the gas being released. I think the gas in this case is the CS2, carbon disulfide. If you've smelled rotten eggs before, that's carbon disulfide. It's a horrendous smelling compound, which is probably a good reason why they won't do it in lab, but I'll see what they can do for you. Okay? So let's actually take a look at the problem and see what's happening here. Okay? So what is the mass of mercury sulfide produced from the decomposition of 1.25 grams of mercury 2 thiocyanate? Okay? I can tell you right off the bat, I'm going to want to do some shorthand here because that's going to be a lot of information to write out. Okay? So what I will do is go over my balanced equation, and instead of writing HGNCS2 every time, I will write, what do you think? What does that mean? Mercury thiosulfate, or thiocyanate. Okay? Whereas over the other one, HGS, mercury sulfide. So that when I go through and do the calculations, I really only have to write 2 letters for my substance unit without having to write out that big long section or sequence of atoms. Okay? Helps as far as calculations go, but it doesn't do much else. So, where do we start our problem with now? Should check the equation, make sure it's balanced. I think I balanced it. Actually, I stole it from the internet, so hopefully they balanced it. Okay. So then we can go and start with what? All conversion problems. Where do we start? What are we trying to get to? We want the grams of our mercury sulfide. What are we starting with? Grams of our mercury thiocyanate. Do our units match? No, what does that mean? We're going to have to do some conversions. I'll go ahead and throw in that number now. We got 1.25 grams of our mercury thiocyanate. Okay. So, start off our conversions. What unit do we want to get rid of? Grams of our mercury thiocyanate. Ideally, we get grams of mercury sulfide. Do we have a way to relate the grams of a substance to the grams of another substance? No. The only way to relate substances, different substances to each other, is through the balanced equation. What units do you have in the balanced equation? Moles, not grams. Okay, so we do not have a way to relate these two, which means everybody's least favorite thing, which is probably why you don't like this method, bust out the eraser and erase the top. Okay? At this point, we now have a couple options on trying to figure out what we should put on top as far as our unit conversion goes. Okay? If you've worked enough problems, okay, or happened to propagate through enough and said, I need to get a substance converted into a substance, and the only unit that I can use to do that is moles, what unit should I put on top? I want moles. Ignore the number. The number is not relevant until we get our unit set up. Okay? So since we know we need to change units, we could say it needs to be moles. Okay? The other method, which I'm not as big a fan of, but it is okay at this stage in the game, is what I would call kind of the shotgun method. Can you convert grams to anything? Okay? Go through all of your possibilities. We have AMUs as a possibility, okay, and we have moles. Okay, really that's it, is just those two options. So if you really have no clue, do one of them. See what happens. Okay? Worst case, you'll end up running an extra calculation that you should be able to fix later on in the calculation stream. Okay? So in this case, we want, whoops, that's an eraser, moles of our mercury thiocyanate. Okay? Since we now have our conversion fact, well, the idea, can we convert between grams and moles? Is that a valid conversion? Yes. Now here's where it gets tricky again. Okay? We want to ignore everything else in this problem. The only thing we are concerned about is the relationship between the grams and moles of mercury thiocyanate. And the reason I address this is that I heard a 2 moles of mercury thiocyanate. Where did you get the 2 from? The balanced equation. That is not part of your unit conversion. Okay? The only thing that you are allowed to look at is the relationship between grams and moles. The balanced equation is irrelevant. What you're starting with is irrelevant. What you're ending with is irrelevant. Where do we find the relationship between grams and moles? On the periodic table. That is the only place you can look. Okay? And I know that's tricky because that unit shows up and we know we have a number that we could throw in front of it. Okay? You must pull that conversion factor from the periodic table because that is the only place that you can get it. How do we determine that number? You're going to have to look up everything. So here I would write out the formula again. I've got HgNCS2. What I want is my grams to moles, or the molar mass. So we would have to go through and look up the molar mass for every single atom within this and add them all up. What's your question?
With the, you don't have to use the coefficient even to figure out this? So
Nope.
would it be 2 mercury?
Nope.
2?
Nope. The coefficient is only there for one reason, to balance the equation. What you are looking at is just that species. Okay? I don't care what's happening to it, or where it came from, or how many I start with. I only care about that one species. Okay? That one formula unit, if you would, in this case, or molecule, or compound. Okay? So we would look up mercury. Mercury has a molecular weight of 200.59. Okay? I'm not going to put units in on this because it's going to be grams per mole all the way through it. What do we then add that to? And actually, I'm going to go downwards for this. Plus 14.01. Where'd you get the 14.01 from? Periodic table for nitrogen. How many nitrogens are there? 2. So we could add 14.01 twice, or we multiply that number by 2. What's the next thing we do? 12.01. Where'd you get that? That's our carbon. Times 2 again. Why times 2? There's 2 of them in our formula. Next one. 32. Again, times 2. We now add all of those numbers up. And those numbers give us, anybody fast enough to have already done that? 360.77? 16. Should get my ears checked. Okay, I'm just going to stick it with the 7 just for the moment. What's the units? So we could use AMUs. That is a valid unit. Okay, but what's the issue behind that? Why do we not want AMUs? What's the mass unit that we're using in our equation? Grams. Okay, so we don't want to use AMUs in this case. We want to use grams. The number goes in front of the grams, and this is the mass per 1 mole. Let's fix our unit a little bit, because our units are still technically wrong in this case. What do we need to fix? It's MT. Ah, that sounds kind of funny. MT, right? MT. We can put our numbers in front, our 1 and our 316.7. What units do we now have? Moles of MT. Is that our answer? No. So what do we have to do? we need to get rid of the moles of MT. Ideally, we would get grams. Okay, go with our target. Our target would be grams of MS. Can we relate the grams of one species to the moles of another species? No. That relationship is invalid. So again, we erase it. And again, we could go through and shotgun. Okay. In this case, we want to, again, think about where we're trying to get. We want to get to grams of MS, which means I need to change the substance unit. The substance unit in this case is moles of MT, so let's change it to moles of that number, thing, whatever that is. Okay? Where do we find the relationship between moles of one substance and the moles of another substance? From the balanced equation. Everything else disappears. The only thing you can look at now is your balanced equation. What number shows up in front of MS? 2. So what number shows up in front of our moles of MS? What number shows up in front of our MT? And in front of our moles of MT? 2. Okay. What happens to our units? Grams of MT cancel. Forgot about that. Moles of MT cancel. And we now have moles of MS. Awesome. We're now into units of MS. But are we at our final answer? No. So again, back to the drawing board. Or board. Why not? Moles of MS we need to cancel. What do we want as our target? Grams of MS. Is there a relationship between the mass and number of things? Yes. Where do we find that? Periodic table. So what do we have to do? Go to the periodic table and figure out the molar mass of MS. Our MS formula was HGS. We do not use our 316 number. Why? That was our molar mass for MT. We're now into units of MS. We have to now go through and calculate that one. We go through and look up our molecular weights for each of these. 5.9 and our 32.07. Add that up and we get 232.66 grams per 1 mole of MS. Okay. We can now slide our numbers in. What number shows up in front of the grams? 232.66. The number in front of moles? 1. What happens to our units? What units do we now have? Grams of MS. What answer did we want? Grams of MS. We have now solved our problem. Okay. A large sequence of individual conversion factors had to go through to do that. Ultimately, you need to be aware of where you can find these conversion factors and only focus on those conversion factors until you can get them set up and put in. You'll notice that I did not worry about anything with numbers. The only time numbers showed up is once I knew what unit I wanted in my calculation. So you have to get that unit set up first, then start to propagate your calculations. Is that a question, Thor? No? Yes?
On the homework I was showing you before class, there was a problem. You said I needed to balance and fix my coefficients.
Yes.
Because the moles in my equations were wrong.
Yes.
So now I'm confused because I balanced the equation and I had a coefficient of 2 on one of the terms. So I put the 2 for my moles in my problem and I got the right answer.
In front of that coefficient. And you would be putting in 2 numbers. Every time you do a mole-mole conversion, there are 2 numbers that go into it. There's the number for your moles of MS and the number for the moles of...
But it was in the first, that one right there. That's
Then you put it in the wrong spot. I'll have to look at your calculations after class. Okay? So it has to go in a particular spot. You might get lucky and accidentally multiply or divide at a different point and still happen to luck into the answer. Ultimately, that's going to be a little bit of luck shining with you. Okay? Other questions? Okay. So what do we end up doing with all of this? This is where it gets into the limiting reactant concept. Okay. As far as the post-lecture questions go, I think there is only one question that is really going to push you on the limiting reactant concept. To go through and do this, we keep coming back to this cheese sandwich kind of deal. We look at our balanced equation, and then we decide how much of each of those reagents do we have, what's the maximum amount of things that we could make out of this. Okay? So let's actually go to a question where we can deal with a balanced equation. If we look at this equation, if I give you 1 mole of this, 1 mole of this, 1 mole of this, how many moles of that can you produce? Okay, so let's check it. What we're saying is given 1 mole of Na2CO3, what do I want? Moles of NaHCO3. Dimensional analysis. Moles of sodium carbonate, and what do I want on top? Moles of our sodium hydrogen carbonate. Is that a conversion factor that I can find? Yes. Where is that conversion factor found? In the balanced equation. So go to the balanced equation. What number shows up in front of our sodium hydrogen carbonate? What number shows up in front of our sodium carbonate? What's our answer? 2. Okay. There's no adding, there's 1, it must go to 1. No, that's what the balanced equation is there for. It allows you to convert between those species. Ideally, you get super comfortable with this and you start to do that conversion in your head. So for instance, if we switch this up, let's go ahead and, can I clear everything? Switch it now to 2, 2, and 2. How many moles of the hydrogen carbonate can you make?
4.
4. I'm not going to accept, oh, okay. What do we start with? 2 moles of sodium carbonate. What do we want? Moles of our sodium hydrogen carbonate. Go to look at your conversion factor. On the bottom, we want moles of our sodium carbonate. Man, I hate writing that out. And moles of our sodium hydrogen carbonate on top. Why did I put those units in those spots? To cancel and get me the target unit that I want. What number shows up in front of the moles of sodium hydrogen carbonate? 2. What number shows up in front of the moles of sodium carbonate? 1. How did you know it was 2 and 1? From the balanced equation. Every single time. 2 times 2 is 4. Okay? So you have to be very careful and use the equation to your advantage. It's not just an add up all the numbers and now we get something on the other end. Okay? There's rules behind what's happening within the equation. You don't need to know those rules, you just need to know how to apply the equation. Okay? One more problem. 2, 1, and 1. How many moles of sodium hydrogen carbonate can I make?
2.
All sorts of fun answers thrown around in here. So let's start with our moles of carbonate. We said 2 of those. We can go through and do our conversion. And if you are not tired writing out the units, I'm going to be very, very upset because I'm tired writing them out. So you better be writing them out, just so you know. Okay? Moles of the sodium hydrogen carbonate, what number needs to show up in front? 2. The other one? 1. The answer would be 4, but you're wrong. Why are you wrong? To go through and solve a limiting reagent calculation, it is not just one species that you have to convert. You must convert every single one of your reactants into products to see what happens. For instance, if we start with our 1 mole of H2O, convert that into our product. What number shows up in front? 2 and 1, and we get an answer of 2 moles. In our first case with our sodium carbonate, we said there were 4 moles of possible product to make. With our water, how many moles of product could we make? 2. Is it possible for me to make 4? No. I run out of water before I can get that reaction to continue. Okay? What we've now found is that water is our limiting reactant. Okay? This problem, thankfully, I simplified it a little bit, but there are officially 3 reactants. We should also go through and check how much product is possible for our CO2. Okay? Thankfully, I picked reasonable numbers, and we get 2 moles as well with that. Okay? So limiting reactant problems are a pain. You must do a unit conversion for every single reactant. Okay? In an individual problem that we've looked at before, when we say we give you 2 moles of sodium carbonate, how many moles of sodium hydrogen carbonate can you make? In that statement, I am implying that there is a ton of H2O and CO2. As soon as I specify an amount of each of those species, you now must go through and calculate for every single one. Your limiting reagent is going to be the one that produces the smallest amount of product. That smallest amount is, oddly enough, the maximum amount you could make. Because at that point, you've lost all of that species. You can't react anymore because you don't have any of that reactant left. Okay? So how does this become even more obnoxious? What if instead of giving you moles, I gave you grams? Can we relate the grams of sodium carbonate to the grams of sodium hydrogen carbonate? No. So what do you have to do? You have to convert to moles. Once you're in moles, then you can convert the substance. Then you can convert and look at your mole amount. Okay? So it requires a lot of calculations to go through and do the limiting reactant type questions. Okay? The ones that you'll see will be relatively simple in most cases. Okay? I gave you one challenging one in the post assignment where you're starting with grams. And I think I gave you a couple other where you're dealing with moles. To go through and do these, you must check every single one. Okay? And the problem here, we said water and carbon dioxide are our limiting reagents. What does that make our sodium carbonate? Makes it our reagent in excess. We have an extra amount of it. Okay? So it's just an extra little name that you can tag on to it. You end up doing the exact same calculations as you would before, except now you just propagate just a little bit more work into it. Okay? I don't remember how many slides exactly I've got here, but starting to push time. Percent yields, even more obnoxious. We're going to propagate this even further, sort of. Okay? To calculate a percent yield, what we're trying to do is report a number or a value that actually makes sense. So if I ran through and did an experiment where I produce, say, gold, okay? And at the end of that experiment, I produce 5 grams of gold versus 500 grams of gold. Okay, which experiment do you think is better? The one that produced 5 or the one that produced 500? It all depends on what you started with. The one that produced 5 grams, I started with 5 grams. That was my starting mass. The one that produced 500 grams, I started with 500 tons. Okay? Which one actually yielded more gold? The first one. Okay? What you have effectively done is normalized your data. And that's kind of the goal of a percent yield. Normalize your results so that you can actually spit out some information that's useful for someone to interpret and use. So what we're doing when we look at a percent yield, it is always your actual yield. How do you find your actual yield? Your actual yield is an experimental value. It is something that you would find in lab. On the test, where would you find the actual yield? It's given to you. Say we yielded 5 grams of gold. Okay? That gives you that value. How do you get your theoretical value? Okay? We do have to divide by it, so we need that number. Where do we get the theoretical value from? That is ultimately a limiting reagent calculation. So our percent yield, to solve for that, we take this new relatively simple formula, but then we have to get our theoretical yield. To get the theoretical yield, we have to do a limiting reagent calculation. To do the limiting reagent calculation, we have to have a balanced equation. Okay? We also need to perhaps convert units. So we have to do everything. Percent yield pretty much takes all of the material from 5, 6, or 6, 7, 8, and 9 and puts it all together into one big problem for you to go through and solve. Right? At its simplest form, this is your calculation. Actual over theoretical. Right? At its more advanced, that theoretical is something that you would have to calculate through a limiting reagent calculation. Okay? Which brings up the next question. What units do we get on a percent yield? Percent. It's unitless. There really isn't a unit associated with it. So when I look at the actual yield, what units would we look at probably in that respect? Grams. Which means my theoretical yield better have what units? Grams, because the percent yield has no units. Those units must cancel each other. Okay, so if our actual yield is in grams, our theoretical yield had better be in grams as well. If our actual is in grams of gold, our theoretical needs to be grams of gold. The substance must be the same as well. Okay? Requires a bit of work to go through and manipulate these. Does it have to be grams? Is the next question. Grams is a way to measure that species. Could we measure the species by counting, say, the number of atoms and relate it as moles? Yeah. So we could do a percent yield where it's the moles of gold over the moles of gold. Okay? That will get you the exact same answer. It is also the exact same amount of work. It's just a question of when you do it. Okay? Pretty sure the rest of these, just combining problems. I do want to real quickly mention 2 last things here. Really not all that important. Empirical formulas. It is the smallest whole number of atoms, whole number ratio within an individual compound. When we look at our ionic compounds, which we've already done, those are always the smallest whole number. But what happens when we move to a molecular compound? Anybody know the formula for benzene? It is C6H6. What's the problem with that? Is that the smallest whole number ratio? No, that can be converted to C1H1. C1H1 is the empirical formula. Why would we use the molecular formula of C6H6? Because to make a compound of benzene, it is not 1 atom of carbon and 1 atom of hydrogen. It is 6 atoms of carbon and 6 atoms of hydrogen. Okay? So that makes your conversion, or that makes the empirical formula ultimately useless. Sort of. What does the empirical formula tell you about benzene? Really, really simple. It's made up of carbon and it's made up of hydrogen and nothing else. That's not a lot of information, but that is some information. That is ultimately what your empirical formula tells you. There is a relationship between the empirical and the molecular formula. What is that relationship? They are related by a whole number. Okay, so you can scale upwards. I do recommend that you go through and look at the rest of the slides, particularly the very last one. That gives you steps on converting between your empirical and molecular formulas, which will help with your post-lecture questions, but it's not a super big issue. Okay? Not something that's all that important, ultimately, because we can't ever really use our empirical formulas. And even the molecular formulas, ultimately, you'll find out are pretty useful. So the quiz is coming around now. You've got roughly 15 minutes to go through and take it. Use whatever notes you've got. You can use your exam.
Why didn't we write for that class?